Assalamualaikum and a very good day. So today me and my partner Nurin Bisharah will be doing a presentation on the topic of a new method based on extraction induced by emulsion breaking for determination of cobalt and nickel in chocolate bars by graphite furnace atomic absorption spectrometry.
Everyone loves chocolate, but what most people do not understand is that the chocolate can contain significant levels of metals that are acquired in their environment, such as nickel and cobalt. Some of the minerals in chocolates are actually beneficial to our body, but others, when taken in excess, may be bad. Due to its complex composition, analyzing metals in chocolate isn't easy. This study introduced a fast and low-cost method using emulsion breaking combined with graphite furnace AAS to detect cobalt and nickel efficiently. Why is it the analysis of cobalt and nickel in chocolate important? Well, either both of these metals are toxic above certain levels. These metals have been shown to cause many forms of health hazards such as allergies, problems to the organs of the body, and even cancer. Such natural metals may naturally make their way into the cocoa beans via soil condition and farming, thus find their way into the chocolate we consume. Chocolate is a product used on a regular basis by children in particular, so even minimal levels over a period of time can be an issue. That is why regulation limits have been established in many countries to regulate the quantities of metal permitted in foods. We can assist in the protection of consumers and also to make the chocolate products suitable and remedials in terms of food safety by analyzing cobalts and nickels.
So, why graphite furnace AAS GFAAS was chosen for the method of analysis? Let us analyze the comparison between GFAAS and other spectroscopic techniques. Firstly, GFAAS is less susceptible to spectral and non-spectral interferences compared to flame AAS, ICP-OAS, as well as ICP-MS. Secondly, low limit of detection can be obtained by GFAAS at similar level to those obtained by advanced technique of ICP-MS. Last but not least, GFAS is characterized by high precision, good compatibility with many techniques for elemental separation, and GFAS also results to a more moderate cost due to the low consumption of gases, low maintenance, and therefore low technical support. So this table presents the analytical performance characteristics for determining cobalt and nickel in chocolate bars using graphite furnace AAS after an extraction process by emulsion breaking. Hence, I will be explaining on some of the important characteristics. The first characteristic determined is linear range. It is the concentration range over which the method provides a linear response. For cobalt, it is between 0.49 to 10 microgram per liter, whereas nickel is between 0.98 to 50 microgram per liter. This means that within these ranges, the absorbance versus concentration plot is linear. The second one is sensitivity, which describes how a small change in concentration is reliably detected. For cobalt, the value is 0.0081 plus minus 0.002, whereas value for nickel is 0.0089 plus minus 0.002. Lower values means higher sensitivity, therefore it can be seen from the values that both are quite sensitive and similar. Next is limit of determination. It is the lowest amount that can be reliably detected but not necessarily quantified. The values will be thoroughly explained in the discussion section. The fourth characteristic is limit of quantification, which is the lowest concentration that can be quantified with acceptable accuracy. For cobalt, it is 1.65 microgram per liter or 82.4 microgram per kilogram. For nickel, it is 3.27 microgram per liter or 163 microgram per kilogram. Lastly, the percent relative standard deviation is a measure for precision for 3 replicates. Precision is generally acceptable, although slightly more variable in sample. The percent RSD will also be explained in the discussion section along with the limit of detection, recovery percentage, and the correlation coefficient.
In this part of the presentation, I will discuss the spectral information obtained in the study and how it was used for both qualitative and quantitative analysis of cobalt and nickels in chocolate samples. Here on the slide, you can see figure 3 from the article. It shows two important things, the temperature optimization curve and the transient signal for both cobalts and nickels. In part A of the slide now, the integrated absorbance compared to temperature. This data was applied in the atomization of the furnace program. To obtain correct quantification, the correct temperatures are necessary so that the metals is completely atomized yet not lost to pyrolysis. Taking into consideration of this curve, the best pyrolysis temperatures were determined at 1000 degrees Celsius of cobalts and 900 degrees Celsius of nickels, and both elements atomized successfully at 2500 degrees Celsius. Thus, since the sample and aqueous standard signal overlap this well, we could use simple external aqueous calibrations and no metric mesh standards were necessary. It is a huge benefit in ordinary analysis. The transient absorbance signals of cobalts and nickels are shown in part B and C of the slide. Correspondingly, these signals were marked during atomization of graphite furnace AS. We noticed that the solid line is the sample extract and the dashed line is the aqueous standard. The most important observation in this is that the peaks of cobalts and nickels in the samples were quite similar to that in the standard solution, as it rightly proved that the identity of the elements and that the chocolate matrix did not interfere with the signal. This match is essential in qualitative analysis as it reveals that it is indeed cobalts and nickel that we are identifying. So now we can see the results. Due to this spectral confirmation, the technique was observed to be very good both in sensitivity and accuracy. The detection limits were low enough to measure trace levels of metals around 25 microgram per kg for cobalts and 49 microgram per kg for nickels. Recovery values were also acceptable, over 90% in both elements. Precision was also good, with values of the RSD is less than 11%, which implies there is a low variation in between the repetition of a test. This makes it evident that the method is trustworthy and that it can be replicated. Lastly, there is the correlation coefficient R that indicates the goodness of fit of the calibration curve. The R is 0.9982 to cobalts and 0.9965 to nickels, which is very close to the value of 1. This indicates that there is an excellent linear relationship, and this method can be used to accurately quantify metals within the given range of concentration.
Despite its advantages, graphite furnace AAS also has its limitations. Some of the limitations include limited dynamic range, no screening ability, element limitation, chemical interferences, slower analysis time, and it only allows 1 to 6 elements per determination. Thus, there are a few ways that could be done for us to improve or to avoid these limitations by GFAAS. In GFAAS, chemical interferences due to the effect can cause the formation of stable or volatile compounds in the atomizer. Interference caused by the formation of volatile compounds can be avoided by modifying the matrix. This could be done by choosing an appropriate temperature for dry and calcination cycle atomization, or by adding a reagent in sample and calibration standard. So the role of the metric is to boost the volatility or to convert the analyte in a less volatile compound. In both situations, the change is made to be adequately different to allow the separation in the ashing state. Other than that, a two-step pyrolysis could be applied to improve the analysis when elements with various thermal behaviors were investigated. Lastly, we could implement inductively coupled plasma technique for simultaneous determination of many elements. In conclusion, the new extraction method developed in this work allows the separation of cobalt and nickel from the chocolate matrix and their determination by GFAAS. In this method, extraction induced by emulsion breaking is combined with two approaches, namely syringe extraction and membrane-assisted separation. When applying the proposed experimental configuration, no centrifuge or microwave digestion method are needed. Instead, the emulsified sample just undergoes simple filtration with nylon syringe filter, and the entire extraction process can be done in approximately 1 minute, which is considered as a fast extraction. The proposed methodology is also simpler than conventional EIEB and MWAD. Furthermore, the method also results to a lower reagent use, hence is safer and more cost-effective. Finally, this method provides high extraction yield and a good precision for cobalt and nickel, in addition to allowing the use of aqueous standard.